Today, we're going to talk about 5 of the most unusual planets discovered recently. Imagine a place where molten lava flows in an endless stream, creating a fiery landscape that glows red from space many light years away. Imagine a world so close to its star that its atmosphere is showered with a rain of vaporized metal. Imagine a giant planet orbiting a star so small that it defies our understanding of planet formation. It sounds like scenes from yet another science fiction movie. However, these are real discoveries that astronomers have made outside our solar system. Why is the planet literally melting from the inside out? What could cause strange light phenomena, including what may be the first rainbow seen outside our solar system? How do the system's tidal effects determine the fate of its planets? And finally, can a distant cold giant turn into a scorching hot Jupiter? Join us as we uncover the secrets of the strangest planets in the universe, each with its own story that could change the way we think about the cosmos. Get ready to encounter TOI 67131, a recently discovered exoplanet that's caught the attention of astronomers for its unusual characteristics. This unique world, located about 66 light-years from Earth, has caught the attention of scientists with its intense volcanic activity and extreme surface temperatures. Discovered by the Transiting Exoplanet Survey satellite, this rocky planet is the innermost planet in its system, orbiting an orange dwarf star. With its size slightly larger than Earth, it completes its orbit in just 2.2 days, resulting in its shape being altered by strong gravitational interactions with 2 neighboring planets. The gravitational pull from these nearby bodies distorts the planet's orbit, giving it an elongated shape that creates a phenomenon described as the perfect tidal storm. This constant attraction leads to intense internal friction and heating, resulting in surface temperatures in excess of 400 F. Upon further investigation, astronomers speculate that the planet's surface is dotted with active volcanoes that are constantly erupting and contributing to the fiery landscape. Globe Stephen Kane, an astrophysicist at the University of California, Riverside, expressed the awe that researchers feel at the prospect of such a planet. Due to its intense heat, it emits light in optical wavelengths, making it visible from space as a glowing sphere, unlike any other exoplanet discovered to date. TOI 67131 offers new insights into how extreme conditions can affect terrestrial planets. The tidal forces operating here are unprecedented. In comparison, Jupiter's moon Io has significant volcanic activity due to gravitational interactions with neighboring moons. However, the object of our attention is subject to tidal forces that are estimated to be 10 million times stronger than on Io, resulting in a completely different and more extreme geologic landscape. Here, volcanic eruptions are not just a spectacular sight, but an opportunity for scientists to understand more about the formation and evolution of planets under extreme conditions. This dynamic behavior opens a window into how energy from both the proximity of stars and gravitational interactions can shape a planet's geological landscape. By measuring the planet's mass, researchers hope to gain insight into its material composition, volcanic activity, and history of formation. Future observations will be crucial to confirm its existence and detailed characteristics. As new data becomes available, this unusual world may change existing models of planet formation and evolution. And now, let's be introduced to the equally amazing ELS 3154b, a massive exoplanet orbiting a surprisingly small star that poses a major challenge to our understanding of planet formation. With a mass about 13.2 times that of Earth, ELS 3154b resembles Neptune, yet it exists inside a planetary system whose host star, ELS 3154, has only 11% of the Sun's mass. The stark contrast raises fundamental questions about how such a large planet could form near such a low-mass star. The discovery of this planet was facilitated by the Hobby Eberly telescope at McDonald Observatory in Texas. Using a cutting-edge near-infrared spectrograph, the researchers found periodic shifts in the spectrum of the star, indicating the gravitational influence of the planet. This allowed them to confirm its existence with observations from NASA's Transiting Exoplanet Survey satellite and the European Space Agency's Gaia satellite. Prior to the discovery of ELS 3154b, it was commonly assumed that low-mass stars mostly form small planets. Observations of other such dwarfs often revealed clusters of rocky planets, such as in the TRAPPIST-1 system, where 7 Earth-sized planets orbit a low-mass star. However, ELS 3154b breaks this paradigm by showing a single imposing planet in a close orbit, suggesting an entirely new formation mechanism. The nature of this planet is suggestive of its formation. Although giant planets orbiting low-mass stars do exist, they usually appear much farther away from their stars, where different processes are at work. In our case, scientists considered the possibility that the planet formed in another system and was then captured by ELS 3154. However, the circular orbit of the planet fundamentally disproves this theory, indicating that its formation most likely occurred within the current system. Researchers turned to the core accretion model, which is traditionally used to explain the formation of planets. The initial modeling did not yield results consistent with the size and orbit of ELS 3154b, indicating that traditional models are not applicable here. Adjustments to the model parameters, in particular increasing the dust density in the protoplanetary disk, led to a breakthrough. A tenfold increase in the dust density provided the necessary conditions for the formation of a planet of similar mass in a close orbit. This realization highlights the potential phenomenon of missing mass in protoplanetary disks. The dust necessary for planet formation may exist in forms or states that modern telescopes cannot detect, raising questions about the material available for planet formation in such systems. One hypothesis suggests that when dust aggregates, it may reach sizes beyond what can be discerned. Alternatively, dust may be continually replenished by scooping it up from the surrounding cloud of material. This discovery prompts a re-evaluation of theories of planet formation. It also emphasizes that planetary formation may be more diverse than previously thought, and suggests that giant planets may indeed form in environments previously considered unsuitable. Another equally unique planet, WASP-76b, often referred to as the Hell Planet, is a prime example of the extreme conditions found outside our solar system. Located about 637 light-years from Earth, this exoplanet has attracted attention for its strikingly high temperatures and intriguing atmospheric phenomena, including the potential detection of a glory, a rare rainbow-colored light show. First discovered in 2013 as part of the Wide-Angle Search for Planets project, WASP-76b has a mass about 90% greater than Jupiter's, but with a diameter only twice as large. Such an enormous size contrasts with its proximity to its host star, where it orbits at a distance about 20 times closer than Mercury is to the Sun. As a result, the planet completes a full orbit in just 1 day and 19 hours, leading to extreme atmospheric conditions. The planet's tidal locking means that one side of the planet is constantly flooded with sunlight, while the other side remains in darkness. The sunlit side reaches staggering temperatures of about 4,350 F. Such intense heat can vaporize metals like iron, creating a unique atmospheric cycle. Vaporized materials can condense into rain on the cooler, darker side. This interaction of heat and atmospheric conditions creates a hostile yet mesmerizing environment. Recent studies have revealed intriguing new data about the atmosphere of WASP-76b. In particular, a bright spot at the boundary between the illuminated and dark sides has been detected. This phenomenon has been interpreted as a potential glory, a rare optical effect characterized by concentric rainbow rings resulting from diffraction. Such a phenomenon has only been recorded within our solar system, making the possibility of observing it on such a distant planet particularly exciting. A glory is formed when sunlight passes through small gaps between atmospheric particles, bending and splitting the light into its constituent wavelengths. The conditions required for this phenomenon are very specific. The particles must be spherical, homogeneous, and stable enough to persist for long periods. The presence of such conditions on WASP 76b, while not certain, would mark a significant advance in our understanding of exoplanetary atmospheres. Despite the possible identification of a glory, researchers caution that the evidence remains preliminary because it is based on an exceptionally weak signal. More advanced instruments, such as those aboard the James Webb Space Telescope, may be needed to confirm this intriguing theory. Further observations could help astronomers determine if this is indeed a glory, thus opening a new chapter in the study of exoplanet. If the phenomenon is confirmed, it would not only be a groundbreaking discovery, but could also serve as a model for studying similar phenomena on other exoplanets. While researchers continue to study WASP 76b and its unusual atmospheric conditions, the possibility of detecting the first known rainbow outside our solar system remains a tantalizing prospect. Meanwhile, let's take a look at another intriguing planetary system that demonstrates the fascinating interplay of gravitational forces and their long-term effects on planetary orbits and environments. This is HD 10467, dated about 20 parsecs from Earth. This system includes a bright K-dwarf star around which 3 separate planets orbit. Interactions between these planets result in noticeable tidal effects, particularly on the innermost of the planets. Initially, a giant planet in an eccentric orbit with a period of about 55 days was discovered in this system. It was later confirmed that this planet, labeled B, has a slightly eccentric orbit. Later observations using radial velocity data from the high-accuracy radial velocity planet searcher and the high-resolution Echelle spectrometer detected an additional planet with a mass close to that of Uranus, orbiting the star every 14 days. In addition, data from the transiting exoplanet survey satellite indicate the presence of an Earth-like planet candidate with an orbital period of about 2.2 days. There are significant dynamical interactions between the planets in the system, resulting in pronounced tidal effects, especially for the innermost of the planets. The eccentric orbits of the 2 outer planets cause changes in the eccentricity of the inner planet's orbit, creating a so-called tidal storm. This phenomenon generates tremendous internal friction and heat within the planet, resulting in surface temperatures that can reach an incredible 2660 Kelvin, or, in simple terms, 4,220 F. The dynamical stability of the HD 10467 system has been thoroughly analyzed with simulations, which show that the system maintains long-term stability over millions of years. Continued studies of tidal effects and planetary interactions may provide insights into the formation and evolution of compact multiplanetary systems. And now, last but not least on our list for today, the exoplanet discovered this year with the complex name you see on the screen offers a glimpse into the dynamic and transformative nature of planetary evolution. This Jupiter-sized planet, located about 1,100 light-years from Earth, has one of the most highly eccentric orbits ever observed. It is currently undergoing a significant orbital transformation, changing from a cold Jupiter to a hot Jupiter over billions of years. Discovered thanks to data collected with the same test mission, the planet was first identified by characteristic dips in starlight as it passed in front of its host star. Subsequent observations confirmed its highly elliptical orbit, which brings the planet close to its star before deflecting it far out into space. The orbit is not only eccentric, but also retrograde, that is, it moves in a direction opposite to the rotation of its star.